Alright, so now we're going to do some practice with the material on aldehydes and ketones. Question 1, we've got some sets of compounds that we're going to rank in order of increasing boiling points. On part A, we've got 3 different functional groups. We've got an ether, we've got a ketone, and we've got an alcohol. And so we've learned that of these 3 groups, only the alcohol has hydrogen bonding. So of what we have here, that's going to be the strongest intermolecular force, and therefore the highest boiling point. Because as you look at these, we see that they all have the same number of carbons, so we can't really use that as a distinction. For the other 2, we have a ketone, which has dipole-dipole interactions, and then we have the ethers, which are primarily just van der Waals forces. So the ethers with the weakest attraction will have the lowest boiling point, followed by the ketone and the alcohol. In question 2, all of these are aldehydes, but the one on the left has 4 carbons, the one in the middle has 7 carbons, and the one on the right has 7 carbons. So based on number of carbons, we know the one on the left will be the lowest. But which one will be the higher of the 2 with 7 carbons? Well, the one in the middle is a straight chain, whereas the one on the right is branched. And we've learned that the more branched the molecule is, the worse the attraction, and therefore the lower the boiling point. Question 2, we have a bunch of compounds. We want to know which ones are water soluble. And we should recall that for things like ketones and aldehydes, it's when we get above 4 carbons, that's when they tend to be insoluble in water. And so smaller molecules such as acetone, acetaldehyde, or formaldehyde, which all have 3 or less carbons, are going to be highly water soluble, whereas 3-hexanone has 6 carbons, benzaldehyde has 7, and benzophenone has 13 carbons. None of those would be expected to be water soluble. Alright, question 3, we're going to predict the products of these reactions. A and B, we have the same set of reagents. These, you may recall, are the Tollens reagent. And the Tollens reagent allows us to oxidize an aldehyde into a carboxylic acid. And since both of these have aldehydes, we will just see those converted to carboxylic acids. Same thing with part C. An aldehyde can get oxidized by the Tollens reagent to form the carboxylic acid. What will a ketone do with the Tollens reagent, as we can see down in part F? So here's our Tollens reagent again, but we have a ketone. Well, it doesn't react, won't do anything. And then D and E, we have one of the reagents we saw in the alcohol chapter, the Jones reagent, potassium dichromate and sulfuric acid. And when we learned about it in that context, we said that what happened was it would take a primary alcohol, oxidize it to an aldehyde, and then oxidize the aldehyde to the carboxylic acid. So if we just started with the aldehyde, could it just do the second half and oxidize that to the carboxylic acid? It can. And so the products of these 2 reactions, D and E, would be basically the same as if we were doing a Tollens reagent problem. That aldehyde can be oxidized 1 time further into the carboxylic acid. In question 4, we have reductions. Aldehydes and ketones can be reduced with hydride, such as sodium borohydride, to form alcohols. In question 5, we're adding alcohols to either aldehyde or ketones. And you could give either the hemiacetal or the acetal as the product. Same thing here in part B. So that would be the hemiacetal, or in this case, since it started from a ketone, the hemiketal. Or on the left here, we're drawing the ketal. Either answer would be acceptable here. Same kinds of things in C and D. And then finally, in question 6, asking for you to draw the structure of the tautomer. Now, if you recall that any carbonyl, especially ketones and aldehydes, under acidic or basic conditions, is in equilibrium with its enol, which is a tautomer. And so that's what we would want to draw here. Draw out the enol. Now in part B, we can't draw an enol. Why not? Well, remember, forming the enol requires that we remove an alpha hydrogen. The alpha hydrogen being the hydrogen on the carbon next to the carbonyl. Well, in part B, these two alpha carbons don't have any hydrogens, so we can't draw a tautomer. It cannot form an enol. But any of these others, as long as there is an adjacent hydrogen, we can draw them.